In this video, we look at some useful concepts and tools that will greatly assist our understanding of chemical bonding. Specifically, we look at the use of Lewis symbols for tracking valence electrons during bonding. We're introduced to the concept of the octet rule, and we look at the property of electronegativity and its effect on chemical bonding. The first concept we'll look into is the use of Lewis symbols. Now, as mentioned in the previous video, the only electrons involved in bonding are valence electrons. For most atoms, the valence electrons are those that occupy the highest energy or outermost shell, that is the shell with the highest N value. So for example, the oxygen atom has an atomic number of 8, has a total of 8 electrons, and 6 of them are valence electrons. The electron configuration for oxygen can be represented as the helium core, with 2 electrons in the 1s subshell, plus the valence electrons 2s2, 2p4. The orbital diagram for the valence electrons looks like this, with 2 electrons paired in the 2s subshell and 4 electrons spread across the available orbitals of the 2p subshell. These valence electrons can also be represented using Lewis valence electron dot symbols, or simply Lewis symbols. And the Lewis symbol for an element consists of the atomic symbol of that element plus a dot for every valence electron. So the Lewis symbol for oxygen looks like this, with 6 dots placed around the O symbol on all 4 sides, top, bottom, left and right. You will note that each side can only accommodate 2 dots or 2 electrons, and they are placed around the atomic symbol individually first before pairing them. This diagram here shows the Lewis symbol for the first 20 elements. The group 1a elements have only 1 valence electron and are therefore represented using a single dot next to the atomic symbol. The group 2a elements have 2 valence electrons and they are placed on either side of the atomic symbol. The group 3a elements have 3 valence electrons and they are placed on 3 sides of the atomic symbol, while the group 4a elements have 4 valence electrons and they are placed as single dots on each of the 4 sides, top, bottom, left and right of the atomic symbol. By the time we get to the group 5a elements, we see the first of the electron pairs around the chemical symbol, with 1 pair of dots and 3 single dots around the 4 sides of the atomic symbol. The group 6a elements have 2 pairs of dots and 2 single dots around the atomic symbol, while the group 7a elements have 3 pairs of dots and a single dot representing the 7 valence electrons in their electron clouds. Finally, we get to group 8a or group 18. These are the noble gases, and we see that with the exception of helium, they have 8 valence electrons represented as 4 pairs of dots around the atomic symbol. Helium, of course, has only 2 electrons. It's a period 1 element and can only accommodate a maximum of 2 electrons in its valence shell. Now, a couple of things to note about this diagram include that elements in the same group have the same number of valence electrons, and we've seen this before, and we should not be surprised by this because elements in the same group share similar physical and chemical properties by virtue of having the same outer shell valence electron configuration. The number of valence electrons equals the group number if we use the old Roman numeral notation for groups. So again, we see here the benefit of using the old naming convention for groups. The maximum number of valence electrons for main group elements shown here is 8. And we see this only with the noble gases, which, as we've noted several times, have stable electron configurations. And we pursue this idea of a stable 8 electron arrangement in the valence shell by introducing the octet rule. Now, we know that the electron configurations of noble gases are the most stable, and we know that atoms tend to gain, lose or share electrons to achieve the same number of electrons in their outermost shell as the noble gas closest to them in the periodic table. The full electron configurations of the noble gases are shown here, and the common feature of all of these configurations is a completely filled valence shell, or more specifically, completely filled S and P subshells in the valence shell, and these are represented in red. In all cases, the number of electrons in the valence shell is 8, with the exception being helium, as we've already noted. This means that atoms undergoing chemical reactions by gaining, losing, or sharing electrons tend to end up with 8 electrons in their valence shell. And this generalization can be summed up by the octet rule. Atoms tend to gain, lose, or share electrons in chemical reactions until they are surrounded by 8 valence electrons. Now, there are some notable exceptions to the octet rule, which we'll consider in subsequent videos, but for now we need to highlight that hydrogen will always be an exception. Hydrogen is a period 1 element and therefore can only accommodate a maximum of 2 electrons in its valence shell. Because hydrogen tends to surround itself with only 2 electrons instead of 8, we can refer to a duet rule for hydrogen if we like, where we will only ever see a duet of electrons surrounding hydrogen atoms in chemical bonds. Because hydrogen can only ever have 2 electrons around it, it will never be a central atom in a polyatomic molecule. It will always be a peripheral atom, and it will always only form a single bond. Now, the last of the fundamental bonding concepts that we'll look at in this video is electronegativity. Electronegativity refers to the ability of an atom within a bond to draw valence electrons to itself. Electronegativity is usually measured on the Pauling scale, which is a unitless scale, where fluorine, the most electronegative element, has been arbitrarily assigned the maximum value of 4. The electronegativity values of all other elements are then measured relative to fluorine, and those values are shown in this version of the periodic table. Differences in electronegativity of elements arise from differences in nuclear charge, differences in size, and differences in the number of non-valence electrons. As a result, some elements have a greater ability to attract bonding electrons to themselves, or in other words, have a higher electronegativity. Electronegativity is a periodic property of elements, and its magnitude generally increases across a period from left to right and increases as we go up a group or decreases as we go down a group. This means that non-metals at the top right of the periodic table, with the exception of the noble gases, have the highest electronegativities, and metals in the bottom left of the periodic table have the lowest values. And this is consistent with our previous observations that metals tend to want to lose electrons in chemical reactions, while non-metals tend to want to gain electrons. So elements with a high electronegativity have a greater ability to attract valence or bonding electrons to themselves compared to other atoms. And the implication of this is that the electron distribution within bonds and within molecules is not necessarily equal. In other words, we often get an uneven distribution of electrons in bonds and in molecules. And this is important because the size and the shape, and in particular the electron distribution of electrons in atoms and molecules, tend to dictate most of the physical and chemical properties. So, for example, let's consider 3 different types of substances: elemental chlorine, which is a molecular element, the molecular compound hydrogen chloride, and the ionic compound sodium chloride. Elemental chlorine is formed from 2 single chlorine atoms, each with 7 valence electrons. When the 2 atoms are brought into close proximity, these 2 electrons are shared across both atoms to form a covalent bond, with the end result that both atoms gain an octet of electrons within their valence shell. In this case, both atoms are identical and both nuclei attract the bonding electrons equally. The result is a symmetrical or equal distribution of electrons between the 2 atoms, and we refer to this type of bond as a nonpolar covalent bond. The hydrogen chloride example is different. A single hydrogen atom has 1 electron in its valence shell, and the chlorine atom has 7 electrons in its valence shell. When the 2 atoms are brought into close proximity, these 2 electrons are shared across both atoms to form the covalent bond, with the end result being that the hydrogen atom completes its duet of 2 electrons required for stability, and the chlorine atom completes its octet required for stability. The difference in this case is that the atoms are not identical and they have different electronegativities, with chlorine being significantly more electronegative than hydrogen. This means that chlorine draws bonding electrons to itself to a greater degree, and the bonding electrons experience unsymmetrical attractive forces. Now, the greater nuclear charge of chlorine means that the bonding electrons spend, on average, more time near the chlorine atom compared to the hydrogen atom, and we've attempted to represent this by placing the two dots closer to the chlorine atom. The end result is that we have an unequal sharing or an unequal distribution of electrons between the two atoms in this bond, and the bond is said to be a polar covalent bond. We can consider the polar covalent bond as an intermediate bond type between the non-polar covalent bond that we saw in the Cl2 molecule and the ionic bond, which is the type of bonding we see in our next example with sodium chloride. Now, the sodium chloride compound is made up of positively charged sodium ions, Na+, and negatively charged chloride ions, Cl-. The Lewis symbol shows that the sodium atom has lost its only valence electron, therefore leaving it with no valence electrons in its outermost N=3 shell. The chlorine atom, on the other hand, has a complete octet in its outermost shell. The bond holding these two atoms together in this case is the result of the electrostatic attraction of the oppositely charged ions, and we refer to this as an ionic bond. The three structures shown on this slide demonstrate the full continuum of bond types from non-polar covalent through to polar covalent through to ionic bonds. And we'll discuss this continuum of bond types in a bit more detail in just a moment. But I first want to illustrate another way of representing the unequal distribution of electrons within bonds. So if we consider that a polar covalent bond, or simply a polar bond, is a covalent bond in which there is an unequal sharing of bonding electrons, and that on average these electrons spend more time near the nucleus of one of the atoms compared to the other. This unequal sharing of bonding electrons in polar bonds is often represented by the use of the lowercase Greek letter delta, and it is used to identify partial charges on atoms. A delta minus symbol on an atom represents a partial negative charge and a relative excess of electron density around that atom. A delta plus symbol on an atom indicates a partial positive charge and a relative deficiency of electron density around that atom. Using this notation, the hydrogen chloride molecule would be represented like this. Now, the hydrogen chloride molecule is neutral overall and has no net charge, but the chlorine atom has an electronegativity value of 3, while hydrogen has a value of 2.1. Since the electronegativity of the chlorine atom is greater, it draws bonding electrons closer to itself and attains a partial negative charge. This leaves the hydrogen atom with relatively less electron density and therefore a partial positive charge. The direction of the polarity in a polar bond can be represented using an arrow with a cross at its other end. The head of the arrow points in the direction of the partial negative charge, and the cross end of the arrow is placed near the atom with a partial positive charge. Now, bond polarity is characterized by differences in electronegativity values, and small differences in electronegativity values mean the bond is relatively nonpolar. Larger differences in electronegativity values mean the bond is relatively polar, and very large differences in electronegativity values mean that the bond is considered to be ionic. Now, it should be noted that no definitive boundary exists between ionic and covalent bonding, and most bonds have both ionic character and covalent character. And we're actually able to quantify the percent ionic character of a bond by using the differences in electronegativity values of the atoms involved in a bond as shown on this table here. And while there's no definitive boundary between ionic and covalent bonding, it is still useful to describe bonds using these labels. And as a rough guide, we can say that bonds where the electronegativity values between the two atoms is greater or equal to 2, we can consider them ionic. If the difference in electronegativity value is between 0.5 and 2, we can consider that bond type to be a polar covalent bond. And if the difference in electronegativity between the two atoms in a bond is 0.5 or less than 0.5, we can consider that to be a non-polar covalent bond. But in truth, the only truly non-polar bonds are between bonds containing identical atoms.